Hey everybody, so welcome back to another video. Um, this time I'm just going to talk about something interesting which I found when I was going through a textbook. It's an analysis textbook, and the name is A Course in Modern Analysis and Its Applications by Graham Cohen, right? Um, well, it's I think that the textbook is good for like a beginners if you want to learn some analysis or some just basics of analysis, then it's a good book. Uh, as you can see in the content, it starts with some introduction to some prelude to modern analysis. So that means some set theory, functions, countability, open set sequence. This is a standard thing that you need to know, uh, like uniform convergence and linear algebra, things like that, just the basic stuff so that you can get started with any higher stuff in analysis. So right away, the next chapter starts with metric spaces, and then fixed point theorem and its applications, and then compactness, topological spaces, norm vector spaces, mappings on norm spaces, inner product space, and Hilbert space. So you can see there are not a lot of topics, but I think some of the topics mentioned here are good, especially the applications. For example, the one that I'm going to talk about is the fixed point theorem and its applications. So right away, let's jump into the problem that we are going to tackle in this session. So, so we all know how to solve a system of linear equations. In linear algebra, if you have taken any linear algebra course, then you know how to solve any system of linear equations. At least theoretically, you can for sure find out whether there's a solution or not, right? Well, numerically, there are a lot of problems that you may encounter if you are trying to find the exact solution, right? But at least theoretically, you know for sure there's a solution on that, right? So how do you do that? So usually you do it using determinants, right? So let me set the context here. So let's write something on the yellow board. So for example, if you have any system, let's say 2x plus 3y equal to 5, x minus 9, y equal to minus 1, right? So this is a simple system of linear equations in two variables. Now, you can actually make this into a matrix form, right? You can actually make it into a matrix form. So 2, 3, 1, minus 9. That's a matrix that you get. You multiply by x, y, and then you get 5 minus 1, right? Okay, so this is a system. Now you know how to solve the system. Actually, you just need to find the determinant of this particular matrix 2, 3, 1, minus 9, right? So the determinant is, in this case, 9 to the, this is minus 18, minus 3. So this is minus 21, right? So this is not zero. So for sure, you know that there's a solution for this system. So what you do, you just invert the matrix. So this is the matrix A. You just invert the matrix, right? And so the solution is xy is equal to A inverse times. So A inverse times, just my video small here. Okay, so A inverse times 5 minus 1, right? A inverse times 5 minus 1. And that's how you get the solution for the system. But, well, you need to find the inverse, right? You need to find the determinants. Is there some other way of finding solutions to a system of linear equations, right? For example, if the system is extremely large, right? And then Gaussian elimination or finding determinants and, things like that, at least manually, it's difficult. Is there some other way to kind of easily find out whether a system has a solution or not, right? Just by looking at the coefficients, like 2, 3, 1, minus 9. By just looking at this, maybe find some number, right, which has something to do with these coefficients, and can I say something like, is there a solution or not, right? that's exactly what this what's being shown here in the textbook as an application of fixed point theorem, and that's really interesting. When I went through it, it's really nice, and I think many of you may be familiar with applications of fixed point theorem, and this is one of those applications. What we'll do is actually set some context. So I'll just briefly go through the proof, and we'll specifically focus on one kind of system. So, this method that I'm going to show you is not applicable for any system. Okay. For example, so the specific conditions that I was talking about, right? Maybe not all systems or not all matrices satisfy that condition, right? Yet that system may be solvable, right? There may be a solution. So this is the system that they have shown in the textbook. What they have done here is interesting. So as you can see, the first equation they have divided throughout by 16 to get this one, right? The second equation, you can see they have divided by 8. Third one, they have divided by 4, right? So essentially, they have formed an equivalent system, right? And these two systems have the same solution. And what they have done is they have constructed the matrix A, right, from the system. And then they have made a new matrix C, which is I minus A, right? I minus A, which is this. Now, the technique is just look at the sum of squares of these elements of matrix C, right? Sum of squares of these coefficients of matrix C. And if the sum of squares happens to be less than 1, in this case, it's the sum of squares is 253 divided by 256, then there's a solution for the system, right? There's a unique solution for the system. And that's amazing. We just need to form this matrix C, I minus A. C is I minus A. Look at the sum of squares. If it's less than 1, then you can say that there's a unique solution for the system. That's really, really cool. But we need to look at the proof, right? So this all comes down to fixed point theorems and contraction mappings, right? So this is like, the standard stuff that you see in basic analysis course. So we'll set some context here. So A is a mapping from a metric space X to itself, right? So here we are focusing on mappings from a metric space to itself, right? Metric spaces, I have covered a video on metric spaces in my channel. You can go watch that. So A is a mapping from X to itself, from a metric space to itself. And A has a fixed point. So what do we mean by a fixed point? A fixed point means that when you apply A on X, you get X, right? So A takes X to itself, right? So that's a fixed point. And what's a contraction mapping? So contraction mapping, it has to do with the mapping A. So this is the condition of contraction. So what that means is once you map 2 points, X and Y, after mapping, if you find the distance between the mapped points, if it's less than the distance between X and Y, right? If it's less than that distance, and how do we mathematically state that? That's what they have done here. It's bounded about by alpha times distance xy, right? So this distance is less than this distance, right? Distance xy, because alpha is between 0 and 1, right? So the distance is less. So it's as if the mapping is shrinking the distance between points X and Y, right? So it's a contraction, right? That's contraction. So it's a contraction mapping. So that's the definition of contraction mapping. So it shrinks the distance. So now, something about contraction mapping. Any contraction map is a continuous function, right? A continuous function or continuous map on X, right? The proof is simple. If you take any sequence Xn, assume that the sequence converges to a point X. Now you just need to show that a of xn, so the axn, the new sequence that you get by applying a to this original sequence xn, that converges to ax, right? So what I'm saying is, if you have xn, it converges to x. Now you create a new sequence axn, right? So you apply a to every point on xn, and you get a new sequence axn. You just show that it converges to x, right? Just show that it converges to xn. So then it's continuous. And that's exactly what they have shown here. They have calculated the distance between axn and ax. And they have shown that this is bounded above by this one by the definition of contraction, and that's less than distance xn x, right? So that means if this term goes to 0, this term will also go to 0, right? So in a way, axn will tend to ax. So it's a continuous map. But the interesting part is what they have shown here about fixed point theorem, right? That's an interesting theorem. So it says that every contraction map, so if you have a contraction map, and if the contraction map is on a complete metric space, so this is important, should be on complete metric space, then it has one and only one fixed point, right? It has one and only one fixed point. So if you know this, we'll be able to solve the initial problem of solving a system of linear equations, right? And we'll get to that. First, we'll look at the proof of fixed point theorem a little bit. Okay, so let's look at the proof. The proof is simple, and the proof, the way they have written down the proof is important because that's the same technique that we'll use to find fixed points. So essentially, what we'll be doing is, if you are given a system of linear equations, you kind of try to transform it into a kind of mapping from space to itself, and then find the fixed point, right? So essentially, you're kind of tweaking the problem of solving a system of linear equations into an equivalent form where you consider that as a mapping and then try to find the fixed point, right? So let me show you what essentially happens. So if you have a system like this, right? If you have a system like this, system of linear equations, you can also write it like ax equal to b, right? Ax equal to b. But you can also write this as in another form by introducing a matrix C, which is the I minus A. I is identity matrix. I minus A is our new matrix C. Then what you do is I minus C times X is B, right? Because I minus C is A, right? So I minus C times X is B. Hence, now if you rearrange this stuff, you get Cx plus B equal to X, right? So this kind of tells us, okay, so this is the mapping that we need to look at. Cx plus B, right, is the mapping we have to look at. So we are kind of trying to look for the fixed point of that mapping, right? Cx plus B is a mapping from Euclidean space Rn to itself, right? It's a mapping from Rn to itself. So, and the mapping is Cx plus B. Now, essentially, if you want to use fixed point theorem, that means you find the fixed point, right? Mx equal to x. If you can find the fixed point, then that solves this, right? Then essentially you're finding the Cx plus B equal to x. That means you have found x which satisfies Ax equal to B, essentially solving the system, right? Solving the system of linear equations. So that's the technique here. But the thing is, you need to show that this mapping is a contraction, right? How do you show that it's a contraction? Well, it's very easy to show it's a contraction. So you're dealing with Rn is a complete metric space, right? So one of the requirements for fixed point theorem is that Rn is complete. So it's a complete metric space. Now, distance between y and z is given like this, right? It's Euclidean metric that we all know how to calculate this one, right? Now, to show contraction, all you need to do is find the distance between my and mz, right? Distance between my and mz, okay? Which is just simple. You just apply the Euclidean metric, square root of summation. This is the jth term, my. This is the jth term of mz, right? mz. My is a vector in Rn. Mz is also a vector in Rn. So just take the jth term, right? You just to essentially do this here, right? And then do some algebra here. It's not too hard. Sum of squares. They have also used something called Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. And I think I've done a video on Cauchy-Schwarz inequality. And what they have found is this, right? Which is, let me pull that up. So what they have found is this one. So distance of my, mz is bounded above by some square root of summation of Cj squared. So sum of squares of that matrix C times distance yz, right? So now it's simple. So if this quantity is less than 1, then it's a contraction mapping. So it's a contraction mapping. It's on a complete metric space. There is a fixed point, right? There is a fixed point, and that means there is an x which satisfies essentially this mx equal to x or cx plus b equal to x. And there you have it. There's a fixed point. And so that means this equation has a solution, has a unique solution, in fact, because the fixed point theorem tells you that there's a unique fixed point, right? There's a unique fixed point. So, well, that's the technique. It's very interesting how just by applying the fixed point theorem, you get the solution for a system of linear equations. Now, the proof of fixed point theorem is also not hard. And the proof is very interesting because how you do it. So the point is to find the fixed point. So you start with some x naught in the metric space, just random x naught. And then you create a sequence, right? How you create the sequence is you start with x naught. You apply a, you get x1. You apply a on x1, you get x2. You apply a on x2, you get x3. So you see how you create the sequence, right? So xn, the nth term, the next term is basically a applied to the previous term, right? So you keep applying that, you get a sequence. Now, so it's a complete metric space. So what does a complete metric space mean? I've mentioned this in another video. So if you have a Cauchy sequence that converge, right? In a complete metric space, if you have a Cauchy sequence, it converges. So the point is just to show that this sequence that we have created is Cauchy. Interestingly, it's Cauchy because, see, by doing some algebra here, using the definition of contraction mapping, you can show something like this. Distance of two consecutive terms in the sequence is bounded above by alpha to the power k minus 1 times distance ax naught x naught, right? Some inequality like this, which you will essentially use to prove that the distance between xn and xm, right? N and m are two, m and n are two, so 2 points, xm and xn. Distance between them is bounded above by this quantity, right? Which is alpha to the power m. Here the n is bigger than m, right? They have assumed n to be bigger than m. Now this term can be made as small as we want because it goes to 0 as m tends to infinite, right? So as your m becomes larger and larger, this goes to 0. So essentially you have shown that this is Cauchy sequence, xn is Cauchy, right? And Cauchy sequence, so it converges. And so, okay, so it converges and it converges to some x, right? So x is the limit of this Cauchy sequence. Now, okay, so there's a limit. Is that a fixed point? Yes, that's a fixed point because you see distance of ax and x is, just use the triangle inequality, distance ax xn plus distance xn x. And, so what's xn? Xn is nothing but a times xn minus 1 and this is distance x and x. And you have this, so this first term is bounded above by alpha times distance x, xn minus 1 because of contraction. This 2 goes to 0, right? Because xn tends to x, right? So the right hand side goes to 0, so that means the left hand side should be 0, right? Left hand side is independent of n, so it should be definitely 0. So distance between ax and x is 0. So ax and x are the same point, right? Now, how do you show uniqueness? It's simple. Assume that there's some other y, some other fixed point, ay equal to y. Now you just need to calculate the distance between x and y. That's nothing but distance between ax and ay, because x is a fixed point, so x is ax, y is ay. That's bounded above by alpha times distance xy, right? This is by contraction, but this is not, so this gives us a contradiction because distance xy, how can it be less than alpha times distance xy, right? Where alpha, because alpha is less than 1. Since alpha is less than 1, this is not possible unless distance xy is 0, right? So you see, distance xy should be equal to distance xy, but you're getting to be less than that, right? And so that's not possible, and so the distance should be 0. So this essentially proves that there's just one fixed point, right? There's just one fixed point. Okay. That's the proof of fixed point theorem. And so okay, so this is an interesting theorem. With that, you have a lot of applications. One of them is solving a system of linear equations, right? And that's essentially what they have done here. So if you have a system like this, you just construct the I minus A matrix, right? And then look at the sum of squares. If the sum of squares happens to be less than 1, then you can say that, there's a solution. Well, not just, so there can be other conditions which you can derive, like not just sum of squares. If you're taking some other metric, so here I have picked the Euclidean metric, right? So we have considered the space Rn with the Euclidean metrics, but you can also have other spaces, right? You can actually consider the d infinity metric, right? The maximum metric, right? If you consider this, you can still create this new space, right? Which is again complete, right? And you can derive some other inequality, basically something like, so distance in the infinity matrix between my, mz is bounded above by something like this, where you have maximum times d infinity y. So then this maximum of sum of CJKs, right? That if that's less than 1, then again you get a contraction mapping, and then there's a fixed point. So this is another condition, right, that you can check. This is interesting, but know that not every system needs to satisfy these conditions, right? Yet it may have a solution, right? Yet there can be a solution. So this is just sufficient condition that if you can find something like this, sum of squares of C, elements of C is less than 1, then definitely there's a unique solution. Okay, so that's it. So this was an interesting little application of fixed points. So, okay, I'll see you next time. Till then, take care. Bye.